Hello there, kids. This is your ma'am Akshita, and I welcome you all to the summary session of the very first chapter of ninth grade. But what is the first chapter of ninth grade? It is nothing but matter in our surroundings. So, in this session of ours, we shall be trying to summarize everything that we have learned in this particular chapter. So, let's begin. So, in our today's session, the targets that we are going to achieve or the concepts that we are going to revise or summarize is matter and its classification. That is, how is matter classified? Then we are going to learn about the physical nature of matter, followed by characteristics of particles of matter, and ultimately we shall be doing states of matter, where we shall be learning how change of states also takes place. And then we'll see how the change of state will take place, followed by evaporation. So let's begin our session. But before we do that, we have to first answer what exactly is matter. Alright, anything and everything that we see around ourselves is made up of matter. But what is matter? Matter is anything that occupies space and has mass. All right, so the food that you eat, okay, the rocks that you see, the air that you breathe, the water that you drink, in fact, both you and I, and not just you and I, but every single thing, every single being, every single little thing that you notice around yourself is made up of matter. And not only is this true for living organisms, but also for non-living beings. All right. So everything in this universe, everything in this universe is made up of a material which scientists have named matter. So that is about matter. That is, whatever we see around ourselves ultimately is made up of matter. And what exactly is matter? Anything and everything that occupies a space and has mass is said to be matter. All right, but it's important that we classify things. Is classification not important? It is. It makes our understanding better. It helps us understand the subject better. So who classified this matter? In the earlier days, when this question had come into being, the hub of knowledge was there in the Indian subcontinent, and that in the European region. In European region, especially the Greeks. All right, now the thing is, they thought about it, and then they came to a settlement that okay, we can classify matter. So how did the Indian philosophers, the early Indian philosophers classify matter? They classified into 5 basic elements and called it pancha tattva. Pancha means 5, tattva means components. Both pancha and tattva are derived from Sanskrit. They are Sanskrit words. Pancha tattva, that is 5 components. What are these 5 components? They are nothing but air, earth, fire, sky, and water. As you can see over here, every being is made up of these 5 components. And the fire tattva, that is the fire element, was known as the Agni tattva. The water element was known as the Jal tattva. The earth element was known as the Prithvi tattva. The ether element, that is the sky, it was known as the Akasha tattva. And the air element was known as the Vayu tattva. So these are the 5 components. And they believe that according to them, everything living or non-living was made up of these 5 basic elements only. Alright. And then the ancient Greek philosophers also had a very similar mode of classification. So with this, we have also understood the classification of matter, the earlier classification of matter. Let's now look at the physical nature of matter. Now, it is very important for us to understand the physical being. Like today or tomorrow, let's say you see me somewhere, you'll be able to identify me based on my physical appearance. You'll be able to say, yes, ma'am has black hair. She happens to wear specs, okay, she has a fair complexion. All of these are nothing but the attributes of my physical appearance. right? Similarly, matter, the physical nature of matter is derived from its particles. The particles it is made up of. They decide the physical nature of matter. And this matter is made up of particles. What are these particles? The tiny entities that make up matter are known as particles. And these particles of matter are so small that we cannot see them through our naked eyes. We cannot see them with our naked eyes. However, these particles, when come together, are capable of deciding the physical nature of matter. We shall see that too. So with this we understand that there is a physical nature of matter, and this physical nature of matter is decided by the particles it is made up of. All right, let's now see the characteristics of particles of matter. Now, what are the characteristics of particles of matter? All right, particles are there. All right, these particles even decide the physical nature of it. But what are its characteristics? They must be having some characteristics, right? So, there are three major characteristics of particles of matter. And it is based on these characteristics that almost every attribute of matter is related to. Alright, so what is the first characteristic? The first characteristic is particles of matter have space between them. Particles of matter have space between them. And the space that is there between them is known as intermolecular spaces. So the spaces that are there between them is known as intermolecular spaces. That is the space between two molecules, two particles. Alright, then particles of matter are continuously moving. That is, the particles of matter have the tendency to move continuously. They keep moving. They don't stay still. Now, this movement can either be moving from one place to another, or it can simply be vibrating at the same position. It can simply be vibrating at the same position. But then there definitely is movement, and this movement is continuous. And where does this movement come from? So that the particles of matter are continuously moving, that is, they possess what we call is the kinetic energy. They have kinetic energy. It is by the virtue of this kinetic energy that particles are capable of moving about. And as the temperature rises, the particles move faster. That is, kinetic energy, Ke here stands for kinetic energy, is directly proportional to temperature. It is directly proportional to temperature. That is, if the temperature increases, the kinetic energy also increases. If the temperature decreases, the kinetic energy also decreases. What does that mean? It means that if the temperature increases, the kinetic energy increases, as a result of which the particles are capable of moving about. And if the temperature decreases, then the kinetic energy also decreases, as a result of which the particles are not capable of moving about. That is, their movement is very less. All right. Now, that is the second characteristic or attribute. Now, what is the third characteristic? The third characteristic states that these particles of matter attract each other. That is perhaps the reason why matter is so intact. All right. These particles of matter, they attract each other. Now, this attraction can be more or less. But then there definitely is attraction between the particles of matter. All right. And particles of matter have force acting between them. Now, obviously, if there is attraction between them, there definitely must be some force that is there between them. So, there is force that is present between the particles of matter, which in turn leads to the attraction between them. Again, this attraction can either be more or less, but attraction is present for sure. All right. Then this force keeps the particles together. As I told you, that matter is intact. How is it intact? It is because of these forces, because they try to hold the particles together. So if we want to break apart particles. If we want to make sure that these particles move away from each other, they are not in the same vicinity of each other, so that if they are in the same vicinity, then there is attraction. We do not want attraction. So what do? We break these forces. This is what you need to keep in mind. The strength of this force of attraction varies from one kind of matter to another. Yes, it varies from one kind of matter to another. How does it vary? We shall see that. So this is about the characteristics of the particles of matter. Now moving on to the next slide, which is states of matter. Now we have understood that, there is some force that is acting between them, and this force decides the strength, okay, whether the attraction is more or less, based on which we get the states of matter. So the states of matter that we see around ourselves is either solid, liquid, or gas. The best example for this is water. Okay, water exists in a solid state in the form of ice. It exists as water and is in the presence of its liquid state. And this water upon vaporization, we can see it in the form of vapors or steam, which is in its gaseous state. So these are the three states of matter, that is solid, liquid, and gas. Let's learn about them in detail. Starting with the solid state. See the table you see, the nails you see, the book you see, the chair you sit upon. Are they not rigid? They are rigid. And we classify them into solids. Why? Because solids have a definite shape. They have a definite shape. Why is it that they have a definite shape? It is because when you look at the solid state, let's say this is a solid state. Alright. Now the particles in the solid state are quite close. They are close to one another. They are close to one another. And what do you observe over here? Since they are close to one another, the intermolecular spaces between them are very, very less. Is it not? As you can clearly see, the intermolecular spaces between them is very, very less. So if I have to highlight the intermolecular spaces, the shaded part in pink is nothing but the intermolecular spaces, in the solid state, So what do we see? That the particles are tightly bound. The particles are close to one another. They are close to one another in distance. So what do we understand by this? That the intermolecular distance or space, intermolecular space is less. Now since the intermolecular space is less, they are quite close to one another. So what do you think will be the nature of its forces of attraction? The forces of attraction, in other words, the intermolecular forces of attraction is going to be high because they are tightly held. They are very close to one another. Can you break a wooden block? No, it's very difficult. Why? Because these particles are tightly held. The spaces are very, very less between them. And that is because of very strong forces of attraction of these solid particles. So based on this, what do we understand? That solids have a definite shape. Alright, solids have a definite shape. They have distinct boundaries and fixed volumes. That is, they have negligible compressibility. Try compressing a wooden block. Will you be able to compress it? No. Why is it so? Because the particles that make up that wooden block are tightly held to each other, okay? And then the intermolecular spaces that are present between these particles are nil to negligible, as a result of which you cannot compress them, okay? And as a result of which they are rigid, they have distinct boundaries, and they have a fixed volume. However, solids have a tendency to maintain their shape when subjected to outside force. Okay, when subjected to outside force, they tend to maintain their shape. However, of course, if a lot of force is applied, so much so that it cannot bear, it breaks. All right, but it maintains, it tries to maintain its shape. All right, and solids may break under force, but it is difficult to change their shape. They might break if the force applied is too high, but then they do not easily change their shape. That is perhaps the reason why they are rigid. I hope with this you have some idea now. It is clear to you about the solid state. So this is exactly about the solid state. Now moving about, there is a question, matter of thought. What is the matter of thought? The first one is, what about a rubber band? Can it change its shape or stretch on stretching? Is it a solid? Now think about it. There is a rubber band, and when you stretch it, it does stretch. It's not like it does not stretch, it does stretch. But then the question is, then how is it a solid? Because solids have a definite shape, right? So basically, yes, rubber band is solid. The only difference is that when you stretch it, let's say there is this rubber band, okay, there is this rubber band, okay, you stretch it, we stretch it. Now when you stretch it, its shape changes to this. Why? Because force is applied on opposite directions. However, once the force is removed, it again gets back to its normal shape. Thereby, rubber band, yes, is a solid. But there is another thing you need to keep in mind. If the force applied is too high, too high, then the rubber band can also break. But that does not mean that rubber band is not solid. It is a solid. Now looking at another matter of thought, which is, what about sugar and salt? When kept in different jars, these take up the shape of the jar. Are they solid? Okay. Now this is a nice question. When we take sugar and we take salt, no matter which jar we keep it in, it happens to take up the shape of that jar. So how is it that it is solid? Well, when you look at sugar, each grain of sugar has a distinct shape. It has a distinct volume. Each grain of sugar. Similarly, each grain of salt has a distinct shape, has a distinct volume. Thereby, no matter which jar you place it in, all right, the shape of that particular grain is going to remain the same. All right, thereby sugar and salt are also solids. Now looking at the next question, what about a sponge? It is a solid, yet we are able to compress it. Why? Now you must have come across this fact, the sponge which is there, it has various holes, various holes in it. Now within these holes, air is trapped. So when you press it, air releases out of it and it happens to be compressed. But it again is a solid. Because the particles that make up the sponge, okay, the particles that make up the sponge have high intermolecular forces of attraction between them. So with this, I think you have understood these questions. All right, moving on then. States of matter. In this, now we are going to look at the liquid state. Water. What is the first thing that comes to our mind when we say liquid? So the water that we drink, okay, as you can see, this water which is there in this bottle has a particular shape. But when I'm pouring it in a glass, it takes up the shape of the glass. So what do you understand by this? That the water which is there, it does not have a fixed shape. Now why is it so? I shall tell you. Now look at this. Let's say this is water. Now the particles of water in comparison to that of solids, in comparison to that of solids, are far off from each other. The particles of water in comparison to that of solids are far off from each other. So the intermolecular forces, the intermolecular forces of liquid, water is an example, right, of liquid is less than that of solids. It is less than that of solids. Why is it so? Because the intermolecular spaces between the particles, the intermolecular spaces between the particles is more than that of solids. All right, and as a result of which, now that the intermolecular spaces are more, which I am highlighting with the pink color, the intermolecular spaces are more in comparison to that of solids, the intermolecular forces are less. And since the intermolecular force is less, the kinetic energy is more, because the particles are far off from each other. Since they are far off from each other, they are not held together by strong forces of attraction. Since they are not held together by strong forces of attraction, they can easily move about. Let's take an example over here. If here I am standing and somebody is holding my hand, okay, will you be able to pull me towards yourself? No. But if nobody is there, let's say somebody is there but is at a far off distance, that person is not able to hold my hand. All right, so now if you pull me towards yourself, I'll easily come towards you, right? Move in your direction. Why is it so? Because there's nobody who's stopping me to move about. Similarly, there is no force. The force is there, but that force is less in comparison to that of solids. Thereby they are capable of moving about. And this is by the virtue of kinetic energy, because the forces of attraction are less. So you need to know a certain few things. That is, if the intermolecular space is more, then the intermolecular force is going to be less, as a result of which the kinetic energy is going to be more. This is the first thing that you should know. And the reverse is also there. That is, if the intermolecular spaces are less, then the intermolecular forces is going to be more, and thereby the kinetic energy is going to be less. This is the relationship that you need to keep in mind. This is the relationship that you need to understand. So now looking at water, liquids have no fixed shape but have a fixed volume. They have no fixed shape. Why? They are capable to take up the shape of the container in which they are kept. Why? Because the particles are loosely held. They will very happily take up the shape of the container. However, the volume remains fixed. If you take 1 liter of water and you pour it in a pitcher which has this shape, and if you pour it in a pitcher which has this shape, the volume of that water will still be 1 liter only. Although the shape of the container is different, the volume is going to be same. All right. So they take up the shape of the container in which they are kept. Yes, we have an idea of this. And liquids flow. They have a tendency to flow. Flow is nothing but movement. They have the tendency to flow. Why do they have the tendency to flow? Because their kinetic energy is more in comparison to that of solids. Why is it more in comparison to that of solids? Because the intermolecular forces that are there are less in comparison to solids. And why is it so? Because the intermolecular spaces that are present between the particles are more in comparison to solids. That is why they are able to flow, because of their kinetic energy, and they can change the shape. That is the reason why they are called fluid, as they are not rigid. That is why they are called fluid, because they are not rigid. So with this, we have understood about the liquid state. Now moving on to the gaseous state. Gaseous state. Now before we understand about the gaseous state, before we understand about the gaseous state, let me first give you a certain few facts about the gaseous state, and then we will do an experiment based on which we will have an understanding. So let's say this is the gas particles. Do you see how far off they are from each other? How far off they are from each other? So what do you see over here? What do you see over here? What do you see over here? That the intermolecular spaces that are there are very, very high. As a result of which the intermolecular forces is going to be less. Alright, the intermolecular forces is going to be less. Thereby, the kinetic energy is going to be very, very high. Now, based on this, we can draw a comparison. This is the intermolecular spaces, beta. What comparison can we draw? The comparison that we can draw is that the kinetic energy of gas is greater than liquids, is greater than solid state. This stands true for kinetic energy. Why? Why? Because the intermolecular forces of attraction is less for gases in comparison to liquids, which is lesser than that of solids. This is with respect to what? This is with respect to the intermolecular forces of attraction. And why is this the case? Because the spaces, intermolecular spaces of gas is more than that of liquids, is more than that of solids. This is the intermolecular spaces. So this is the order. This is the order. As a result of which, gases are capable to take up the space of an entire room. Alright, they're capable of taking up the space of an entire room because they have that great a kinetic energy. They can fill up a small bottle. A volume of gas that can fill up a small bottle can also fill up an entire room. Alright, so now look at the experiment. So we have understood a little something about solids, liquids and gases. Now let's look at the experiment. So we are taking 100 ml syringes and we are closing their nozzles by rubber cocks. Okay, so we are closing their nozzles by rubber cocks. Now we remove the pistons from all the syringe. This is a piston. Okay, this over here which you see is a piston. We remove the piston, leaving one syringe untouched. Okay, so we are taking 3 syringes. Okay, we are corking their nozzles, alright, and we are removing the pistons of 2 syringes, and 1 syringe we are leaving it untouched. Alright, and we fill water in the second, okay, and pieces of chalk in the third. Okay, so there are 3 syringes that we have now. Okay, we have 3 syringes, we end up having 3 syringes now. So there is 1 syringe. Okay, there is 1 syringe. There is another syringe, and then we have the third syringe. So in one, we are filling it up with chalk. We are filling it up with chalk. The other, we are filling it with water. And the third, we are leaving it untouched. Okay. So what are they saying? Alright, you are filling the second with water, third with chalk. Okay. Now insert the pistons back into the syringe. Okay. You may apply some Vaseline on the pistons before inserting them into the syringes for their smooth movement. Okay. Now try to compress the content by pushing the piston in each syringe. What do you observe? Now, beta, when you look at these syringes, what do you observe? This chalk is nothing but, if I have to determine its state, solid. Right? Water is nothing but liquid, And this which is untouched, it has nothing but gas. Right? Now we are trying to compress the syringe. Now we know for a fact that solids cannot be compressed. They are rigid. So no matter how much force you apply, you will not be able to compress it. Water, to some extent, you will be able to compress it. To some extent. Okay, after the movement, the piston which was over here, this is the piston, this is the piston, this is the piston. After compressing it, the piston still remains here. It does not change its position. That of water, it comes still here after compressing. After compressing. But that of gas, it comes down to the bottom. It comes down to the bottom. What do you understand by this? That gases can be compressed. That is what we are trying to observe in this particular experiment. All right then. So now let's understand the gaseous state. It is now going to make more sense, which is gases are highly compressible as compared to solids and liquids. Due to its high compressibility, why is it compressible? Because it has large intermolecular spaces. Large volumes of gas can be compressed into a small cylinder and transported easily. The oxygen cylinders that you see, right? They're able to compress large amounts of oxygen into that small cylinder. Why is it so? Because gases are compressible. You can very happily and easily compress gas. Why is it so? Because they have large intermolecular spaces. Then, due to high speed of particles and large spaces between them, gases show the property of diffusing very fast into other gases. So now they have high speed. Why do they have high speed? High speed, that is, they are moving fast. Why are they able to move fast? Because they have high amounts of kinetic energy. Where are they getting this high kinetic energy from? From the low intermolecular forces of attraction. All right, they have low intermolecular forces of attraction. Where is this again coming from? Because of its large intermolecular spaces. Thereby, since they have large intermolecular spaces, as a result of which they have low intermolecular forces of attraction, thereby having large kinetic energy. That is why they can diffuse, they occupy large spaces and they can diffuse very fast into other gases. Thereby, in the gaseous state, the particles move about randomly at high speed. They randomly move about. Also, due to this random movement, the particles hit each other and also the walls of the container in which they are kept. All right. And this on the walls in the container, when they're hitting, okay, they're exerting some pressure. This is how we calculate the pressure of gases. So, the pressure exerted by the gas is because of this force exerted by gas particles per unit area on the walls of the container. So this is about the gaseous state. And we know pressure is nothing but force per unit area. This force per unit area is determined by the force with which the gas molecule or the gas particle is striking the wall of the container, okay, per unit area, by which we can calculate the pressure. So with this, we have understood about the gaseous state. Now moving on to our next topic. Very important and very, easy to understand if you have understood intermolecular force, intermolecular space and kinetic energy. If you have understood these three and their relationship, this is very easy to understand and it also is very important. So can matter change its state? Now this is a question, which is there and you need to find the answer of it. Well, let me give you an example. You know water, right? Water is in its liquid state. Right, that is the state of water. But water can be converted to steam or vapor, which is its gaseous state. And water can also be converted to ice, which is its solid state. So with this, we have understood that yes, matter can be converted from one form to another. How? Let's see. See, we all know from our observation that water can exist in 3 states. That is solid in the form of ice, liquid in the form of water, and gas in the form of vapor. What happens inside the matter during this change of state? Now, something must be happening inside the matter. With inside the matter, that is between the particles of matter. I told you, it is this particle which determines the state of matter, its physical appearance. The state is nothing but its physical appearance, right? Whether it is solid, liquid, or gas. That's its physical appearance. So, it is this particle that will determine its particular state. So, what changes are happening in these particles of matter is what is going to lead us to understand how the change takes place. Let's see. And what happens to the particles of matter during the change? Something must be happening. So, how does this change of state take place? That is what we shall try to answer now. So, what happens is once you increase the temperature, okay, once you increase the temperature of the solid, the kinetic energy of the particles increases. Okay, so what happens is once you increase the temperature, we know temperature and kinetic energy is directly proportional. That is, if you increase the temperature, the kinetic energy will automatically increase. So once you increase the temperature, the kinetic energy will increase between the molecules. As a result, the force of attraction which is holding them together is going to break. Okay, they're going to break this force of attraction. So due to the increase in the kinetic energy, the particles start vibrating with greater speed. The energy supplied by heat overcomes the force of attraction between the particles. Understood? So what happens is the solid particles are held together by strong forces of attraction. We are continuously supplying heat to it. We're continuously supplying heat to it. When you're continuously supplying heat to it, the kinetic energy increases. Now the excess of heat which is being supplied, what happens to this heat? This heat tries to break the force of attraction which is there between the particles. Alright. And what happens is the particles leave their fixed positions and start moving more freely. They start moving more freely. Now with the fixed positions that they had, by the virtue of the strong force of attraction which held them together, kept them at one place, now since that force is broken, they are capable to move about randomly, freely. And a stage is reached when the solid melts and is converted to liquid. At one point, the solid converts to liquid. At one point, the solid converts to liquid. What is it known as? Melts. That point at which the solid is converted to liquid is known as its melting point. So the minimum temperature at which a solid melts to become a liquid, minimum temperature at which a solid melts and becomes liquid is known as its melting point at atmospheric pressure. So let's now look at melting point. So again, the definition, this is the definition of melting point, okay? So it is the minimum temperature at which solid melts to give rise to liquid at atmospheric pressure is known as melting point. So what do you have to keep in mind? The minimum temperature, the lowest temperature at which a solid is converting to liquid, okay, at atmospheric pressure is known as its melting point. The melting point of a solid is an indication of the strength of force of the attraction between the particles. Now this is very, very important. More is the forces of attraction, more amount of heat is required for them to break. Agreed? Agreed. More is the force of attraction between the solid particles, more amount of heat is required to break these forces. Now when more amount of heat is required to break these forces, then don't you think that the temperature is also going to be high? Because as you're providing heat, the temperature is also increasing, right? Thereby, it gives us the melting point. Higher is the melting point. Understand that the forces of attraction are also high. Lower is the melting point. That is, the force of attraction is less. Alright. So the melting point of ice is 273.15 Kelvin. The process of melting, that is change of solid state into liquid state, is known as fusion. Okay, change of solid to liquid state. The solid state to liquid state. What is this process known as? This process is known as fusion. All right then. So now what is Kelvin scale? Kelvin is the SI unit of temperature. 0 degrees is equal to 273.15 Kelvin. That is, if you have temperature in Celsius scale. So how do you convert? So the temperature in Kelvin scale is going to be nothing but the temperature in centigrade scale plus 273. That is how you get temperature in Kelvin scale. Now if you have to find out that for centigrade scale, then minus 273. You will get it in Celsius scale. This is the conversion beta. So for convenience, we take 0 degrees as 273 Kelvin. We are rounding off the decimal. Alright. So to change temperature on the Kelvin scale to Celsius scale, you have to subtract 273 from the given temperature. And to convert temperature on the Celsius scale to the Kelvin scale, you have to add 273 to the given temperature. So with this, we have also understood how to go about conversion of Celsius to Kelvin and Kelvin to Celsius. Now there is a beautiful question, a question that is knocking your thought. What is it? When a solid melts, its temperature remains the same. So where does the heat energy go? So where does the heat energy go? So what happens is, when you are providing the heat, you're providing the heat. Once it reaches its melting point, now no matter how much heat you provide, the melting point remains the same. That does not differ, or that does not go any change. Why is it so? Because of latent heat. See, during the experiment of melting, the temperature of the system does not change after the melting point is achieved, till all the ice melts. So ma'am, where is that heat energy going which I am providing? If I am continuously providing heat energy, the temperature should rise. Why is it that the temperature not rising? This happens even though we continue to heat the beaker. Why? Because this heat, very important point, this heat gets used up in changing the state by overcoming the force of attraction between the particles. So now no matter how much heat you apply, all the heat is then utilized to break the forces of attraction in the bulk of the particles of that particular matter. Clear? So as this heat energy is absorbed by ice without showing any rise in temperature, it is considered that all the heat which is being provided, okay, gets hidden into the contents of the beaker and is known as latent heat. It is known as latent heat. Ma'am, latent heat, ma'am. New term? Don't worry. The term latent means hidden. The term latent means hidden. It is hidden. Where is it hidden? That despite all the energy that is being provided, instead of increasing the temperature, this energy is used to break the force of attraction. It is hidden. It is silently breaking the forces of attraction without causing an increase in temperature. So the amount of heat energy that is required to change 1 kg of a solid into liquid at atmospheric pressure at its melting point is known as latent heat of fusion. I'll repeat again. So the amount of heat energy that is required to change 1 kg of solid into liquid at atmospheric pressure at its melting point. Now what all do you have to remember? You have to heat 1 kg of a solid. So 1 kg of a solid is converted to liquid at atmospheric pressure at its melting point is known as latent heat. 4 things. Alright. So particles in water at 0 degrees centigrade have more energy as compared to particles in ice at the same temperature. Okay. Particles in water at 0 degrees centigrade have more energy than particles in ice at the same temperature, because these particles of water have latent heat of energy in them. All right now. Now, what happens in case of water or in case of liquid state? What happens in case of liquid state? Again, to this liquid state, we are providing heat. Okay? Now, when you're providing heat, it is increasing the temperature. When you're increasing the temperature, the kinetic energy increases. The kinetic energy increases, it starts vibrating, okay? And it starts vibrating. And when more heat energy is released, more heat energy is given, what happens? The force of attraction which are there between the particles, they break. And these particles at one point, they start to convert from liquid state to the gaseous state. So what is that point called? So the temperature at which the liquid starts changing into gas, that particular temperature at which it starts boiling it at atmospheric pressure is known as its boiling point. And boiling is a bulk phenomena. It takes place for the entire system of liquid. So the particles on the bulk of the liquid gain enough energy. Despite, see, once it reaches its boiling point, you're continuously providing heat. Where does it go? This heat energy again is the latent heat of vaporization. And this latent heat, what does it do? It breaks the force of attraction that are present between the molecules. Alright, so particles from the bulk of the liquid gain enough energy to change into the vapor state. So for water, this temperature is 373 Kelvin. And this process of change of liquid to its respective gaseous state is known as vaporization. So what have we understood so far? What is the inference that we can draw from here? It is that the state of matter can be changed into another by changing the temperature. So for liquid, if I have to convert solid into liquid, I have to increase the temperature. And if I have to convert liquid into gaseous state, I have to increase the temperature. However, if I have to convert the gaseous into liquid state, I have to decrease the temperature. And if I have to convert the liquid into solid state, again I have to decrease the temperature. I hope it's clear with this. Now moving on. What is sublimation? Ma'am, solid changes to liquid, liquid changes to gaseous state. But there is a condition where solid directly changes to liquid, there is a condition where solid directly changes to gaseous state without forming the intermediate liquid state, which is nothing but sublimation. That is, a change of state directly from solid to gaseous state without changing into the liquid state is known as sublimation, and the direct change of gas to that of solid is known as deposition. And the best example which you can see is camphor, okay, dry ice, okay, and all the air fresheners that you see, all of that. And this is a solid air freshener. All right, so these are nothing but the examples of sublimation, and this is about sublimation. Now, what is the effect of pressure, ma'am? We have understood that temperature has a role to play when change of state comes into picture. Okay, great, got it. When you are increasing the temperature, it is converting to, solid is converting to liquid, liquid is converting to gas. We are decreasing the temperature, then liquid is forming solid and gas is forming liquid. Okay. But does pressure have a role? And if yes, what? So yes, pressure does have a role. Okay, pressure does have a role. And when we apply pressure, what happens? Alright, so what is the effect of change of pressure? What is the effect of change of pressure? Now when pressure is applied, what happens is when pressure is applied, now imagine there is a gas that is there and you're constantly applying pressure. When you're constantly applying pressure, these gas molecules, don't you think they come close to each other? They do, right? But when the gas molecules are coming close to each other, what is happening? The particles are coming close to each other. And in gases, the particles are far off from each other. So it gets converted to liquid state. liquid state. So that is what is going to happen. So when applying pressure and reducing the temperature can liquefy gases. Have you heard of the solid carbon dioxide? Okay, it is stored under really high pressure. Solid carbon dioxide gets converted directly to gaseous state on decrease of pressure to 1 atmosphere without coming into its liquid state, This is the reason that solid carbon dioxide is also known as dry ice. It is also known as dry ice. So what happens is you continuously keep applying pressure, Now when you continuously keep applying pressure, what happens is when you continuously keep applying pressure, what happens is the gas is converted to liquid and liquid is directly converted to solid. All right. So thus we can say that pressure and temperature determine the state of substance, whether it will be solid, liquid or gas. So with this we have understood the effect of pressure. Now trying to understand evaporation. Evaporation is something that we have come across and we see it. We see water is evaporating. What exactly is evaporation? Evaporation is nothing but water when left uncovered slowly changes to its vapor. The best example is wet clothes. You wet your clothes, you wash your clothes, and these wet clothes, when you keep them for drying, do they not dry up? They do. How? Because of evaporation. So what happens in this case? So we know that particles of matter are always moving and they are never at rest. And at a given temperature, any gas, liquid or solids, there are particles with different amounts of kinetic energy. And in the case of liquid, small fraction of the particles at the surface having higher kinetic energy, they break away from the forces of attraction that are there and get converted into their respective vapors. This phenomena of change of liquid into its vapors at any temperature below its boiling point, below its boiling point is known as evaporation. So this is about evaporation. So now when you take 5 ml of water in a test tube and keep it near a window or under a fan, what are you going to observe? Then you take the 5 ml of water in an open china dish and keep it near a window or under a fan. And when you take 5 ml of water in an open china dish and keep it inside a cupboard or on a shelf, what do you observe? So what happens is when you take 5 ml of water in a test tube and keep it near a window or a fan, eventually evaporation is going to take place, but it's going to be slow. However, when you take an open china dish, what is going to happen is this open china dish which is there, it has a larger surface area, as a result of which the evaporation is going to be really high and really fast. Now moving on to the next one, that is when you take water in an open china dish and keep it inside a cover. Now when you're keeping it inside a cupboard, do you think evaporation is going to take place? Well, evaporation will take place, but it's going to be very less. Okay, it's going to be very less. Why? Because in this case there is no medium of heat energy. There's no medium of increasing the temperature which is able to break forces of attraction between the particles of the water or the liquid. So what are the different factors which affect it? First one is temperature. So when temperature is applied, when temperature is there, when the temperature increases, rate of evaporation increases. Why? Because when the temperature increases, kinetic energy increases, and it is easier for the particles of matter to get converted into their vapor when the kinetic energy increases. Next is surface area. Now more is the surface area. So it has larger area from where it can get evaporated, the vapors can be formed. Thereby, more the surface area, more is the rate of evaporation. That is why when you're drying your clothes, You spread them apart. You spread them apart for their easy drying, early drying due to faster and higher evaporation. Now, humidity. See, at a given point, the atmosphere can hold only a certain amount of water vapors in its vicinity, in itself. Humidity is nothing but the amount of water vapors in a given atmosphere. So now what happens is when there's already enough water vapor in the atmosphere, this upon evaporation, water upon evaporation is going to form vapors only, right? But when there is already enough water vapor in the atmosphere, it decreases the rate of evaporation. It decreases the rate of evaporation, followed by wind speed, That is, when the speed of the wind is more, the water vapor which is present in the atmosphere or in the vicinity is carried away to far off distance, as a result of which the evaporation increases. So these are the factors which determine the evaporation, the rate of evaporation. Now, what is the difference between evaporation and vaporization? Are they different? Yes. The very important difference is that evaporation is a liquid change to its vapors at temperature below its boiling point. Vaporization is liquid is changing to its vapors at its boiling point. Another thing is that this evaporation is a surface phenomena, but vaporization is a bulk phenomena. It is a bulk phenomena, and evaporation takes place at all temperatures, whereas vaporization takes place only at a fixed temperature, which is nothing but its boiling point. So these are the three major differences between evaporation and vaporization. Now, evaporation happens to have an effect of cooling. See, what happens is, in an open vessel, the liquid keeps on evaporating. So the particles of the liquid, they absorb the energy from the surroundings, right? They absorb the energy from the surroundings to regain the energy lost during evaporation. This absorption of energy from the surroundings is going to make the surroundings cool. For example, when you drop acetone on your hand, or on your palm, what happens? The particles gain energy. On our palm, and what happens is they gain energy, or on our palm from the surroundings, and they evaporate, causing a cooling effect. Similarly, after a hot sunny day, people sprinkle water on the roof or open ground, because the large latent heat of vaporization of water helps to cool the hot surface. So evaporation has a cooling effect. So with this, we have come to the end of our chapter. So what all have we learned today? We learned that solid can convert into liquid, and liquid can convert into gas, and solid is converting into liquid when we increase the temperature. Liquid is converting into gas when we increase the temperature. Solid can directly be converted to gas, and that is sublimation. All right. Gas can directly be converted into solid, that is deposition. Then we also learned that gas can be converted. Let me take a different color for this. Gas can be converted to liquid by decreasing the temperature. Liquid can be converted to solid by decreasing the temperature. So this is what we have learned in our session today. We also learned that matter is made up of particles, and matter is nothing but anything and everything that happens to occupy space. So with this, I would now like to do a certain few questions with you. The question is, Seema visited a natural gas compressing unit and found that the gas can be liquefied under specific conditions of temperature and pressure. While sharing her experience with friends, she got confused. Help her to identify the correct set of conditions. So which among these do you think is going to be the correct set of conditions? So she knows this is that what happens is the gas can be liquefied. Now how can a gas can be liquefied? So for a gas to be liquefied, the first thing is that the temperature should be low. All right. and the pressure should be high. So the answer for this is low temperature and high pressure. Now moving on to the next question. During summer, water kept in an earthen pot becomes cool because of the phenomena of. Whenever you see cooling comes into picture. Whenever cooling effect comes into picture, the answer is going to be evaporation, because the application of evaporation is nothing but cooling effect. Now moving to the next question. For any substance, why does the temperature remain constant during the change of state? The answer for this is very easy. That is nothing but latent heat. The answer for this is nothing but latent heat. A very direct question. A very, very direct question. So during the change of state of any matter, heat is supplied to the substance. The molecules of this matter use the heat to overcome the forces of attraction which are present between the particles. And at this period of time, the temperature remains constant. This extra heat acquired by the molecules is used to break the forces of attraction between them, and is known as hidden heat, thereby called latent heat, to change from one state to another. So with this, we are done with our summary, and I would now like to thank you all for being a part of this session. All right, keep studying, keep learning, keep revising until we meet next. Till then, bye-bye.